Hello everyone, I am Susil Kumar Pati. I would like to have a lecture on fluid inclusions. We will discuss about the basic principles of fluid inclusions and their applications in the study of crystallization history of different minerals. Let's know first what is a fluid inclusion. A fluid inclusion is a minor bubble of fluid that was trapped inside a crystal at some stage of its history. These are the paleofluids that was trapped either during the growth of the crystals or after the growth of the crystal by some of the imperfections or due to some deformations. And, these fluids were trapped within some of the crystals. So accordingly, there will be different types of fluid inclusions that we will be studying. Well, based on the origin of the fluid inclusions, we can classify them into three categories. They are primary, pseudo-secondary, and secondary. The primary fluid inclusions are trapped during the growth of the crystals. So how we can know that these are trapped during the growth of the crystals? As we can see in this diagram, these are the primary fluid inclusions, and they are almost parallel to the edges of the crystals. So this gives us an evidence that these are trapped during the growth of the crystals. But the second ones, the pseudo-secondary fluid inclusions, are trapped along the fractures and some of the cracks formed during the growth of the crystals. We know that no crystal is perfectly created. There are some imperfection in most of the crystals. So due to these imperfections, there will be some cracks or some fractures along along which some of the fluids can enter into the crystals and they are entrapped within them. Uh, we can know that how these fluids are entered. So we can see in this diagram that they are not exactly parallel to the edges of the crystals, and they terminate along some of the crystal edges. So these are not exactly during the growth of the crystals, but nearly of the same as that of the primary fluid inclusions. And the last one, the secondary fluid inclusions, they are formed after the growth of the crystals. I mean, as you can see, these are the secondary fluid inclusions. These are formed along some of the cracks that were created after the growth of the crystals. Okay, so these are also known as transgranular fluid inclusions, and they are intruded along some of the cracks that are formed due to some deformation activities. But we will use only the primary fluid inclusions to study the crystallization history of different minerals, because these are actually formed during the growth of the crystals. Well, to study the basic principles of fluid inclusions, we have to take some assumptions that was proved before. So the first assumption is the inclusion fluid was trapped and sealed as a single homogeneous phase, that is proved by apparently same phase ratios. When we take some of the samples of fluid inclusions in the laboratory and heat them to a particular temperature, they they are converted into a single phase. Either the, as we can see in this figure here, the vapor bubble is contracted with increase in temperature and the total phase becomes liquid, because it is a liquid state entrapment. But when there is some vapors inside liquid, and with the increase in temperature, the size of the vapor increases and the total phase becomes vapor, that will be called as vapor state entrapment. In nature, the fluid is entrapped as a single phase, and with cooling they are converted into some vapor. But in the laboratory, when you do the reverse thing, I mean when we heat them, they are either converted into liquid or vapor, depending upon whether it's a liquid state entrapment or whether it's a vapor state entrapment. Well, the host mineral which hosts the fluid inclusions, there will be no change in the volume. The volume of the host will not change, but the volume of the fluids that were entrapped within that host, that might change with decrease or increase of temperature, but there will be no change in the volume of the cavity. Here cavity means to the host mineral in which the fluids are entrapped. When the fluids are entrapped within the cavity, there will be no exchange in the mass with the outside of the cavity. So we can call them as a closed system, and there will be some exchange of heat. So these are not exactly isolated, but they are called as a closed system. After sealing or entrapment of the fluid, there will be no change in mass, but there will be some exchange in heat with cooling of the mineral. Now the fourth one is we can know the origin of the inclusions by studying the petrography of the rock and the minerals in which the fluids are included, whether it's a primary fluid or it's a secondary or pseudo secondary. We can know that. So as we can discuss that in the second point, there is no change in volume. So we can say that there will be no effect of pressure, or whether there is some pressure, but there is no effect of pressure. So we can call them as isochoric system. How we can say that? Because there is no change in volume. If there is no change in volume, so what will be the effect of pressure? Whatever may be the pressure, we can know them by studying the thermobarometry, but we can neglect also them. Now we will discuss about the mechanism of trapping for primary fluid inclusions. The primary fluid inclusions, they are trapped during the growth of the crystals. The crystals might be exactly planar surface, but they can also have some rough surfaces, because no crystal is perfectly developed. All the crystal have some imperfections, and some of the crystals might have rough surfaces and some have exactly planar surfaces. I mean the surface can be smooth depending upon the cooling rate. And as we can see here, the the fluids in case of the well-grown crystals in this cube, the fluids come in contact with the edges of the fluid and some of the faces of the fluids, and it cannot easily intrude through them, but it comes in contact with the edges and the faces of the fluid. So these are most vulnerable to the fluid inclusions. But in the case of the fluids having rough surfaces, the fluids will be entrapped in the angular reentrants. As you can see, the yellow ones in these rough surfaces, the fluids are entrapped in the angular reentrants that captures the fluid. In these methods, the crystals can occupy some of the fluids, and fluid inclusion is mostly favored in case of crystal imperfections. So these are some of the important topics to be covered in this chapter, and if I am given the opportunity to cover it, I am very excited to do this job.